This lecture is going to pick up where we left off in lecture 14, where we had just derived an energy balance for a jacketed batch reactor, where the jacket temperature is approximately equal to constant. And that was that dt was equal to the heat transfer coefficient times the rate times the difference in the temperature between the jacket and our reactor, plus essentially the heat of reaction times the rate that the reaction occurs, and then divided by something that was like the heat capacity of all of the species. And we're going to try and apply this to two different cases. And I thought it would be interesting for us to do that in a way where we actually revisit a couple of concepts that we had a few lectures ago, and that was yield and selectivity. So we're going to revisit those problems and do them in the context of a batch reactor. So here, let me bring up the first problem that we are going to solve today. And here we have two reactions that are happening in parallel to one another. The first one is A goes to B, and K1 here is the same reaction rate constant that we had in our in previous lecture 6, except we weren't given a temperature. We were just assuming that that was the reaction rate constant. So this time we know that that's the reaction rate constant at 250 degrees C. We also have the activation energy for this reaction. We also have delta H of reaction. We're going to assume, for simplicity's sake, that it is approximately equal to a constant over the temperature range that we're interested in this problem. The other reaction that we have is A goes to C. Again, we have the same K2 that we had in lecture 6, and we're assuming that that's at 250 degrees C. We have the activation energy for that reaction as well as the approximately constant enthalpy of reaction, which is 164 kilojoules per mole. So we're going to assume the same initial concentration that we start off with a 2 mole solution of A. Now, we know in our problem, based on our derivation, we're going to need a little bit more information than we had the first time that we solved this problem. So one is about the fluid. So that way we can make some simplifying assumptions about the number of moles and that sort of thing. So we're going to assume that we're basically just in water, right? It's a 2 mole solution that is aqueous, so it's overwhelmingly water. And we're going to assume then that because we have things that are dissolved in water, the heat capacity is a little bit higher. So we'll have a density very similar to water, and that the heat capacity is always 10% higher than liquid water. So I'll show you how that's going to get implemented in a minute. The other thing that we're going to assume is that we start the reactor cold, right at room temperature, which is 25 degrees C. We then, of course, need the heat transfer coefficient and the area. So the product of that we'll assume is 260 watts per Kelvin, which is consistent with what we looked at in lecture 14. And the jacket is being warmed at 250 degrees C by an oil that's running through that. Okay, so let's start to go through this and figure out, how we might solve a problem like this. And before we had started with non-isothermal reactors, we did the exact same thing for every system, right? We said, well, we know that we have A goes to B at K1, and we know that A goes to, say, C with K2. So the first thing that we would do in this case is to determine the rate laws for each of these species. And of course, RA is equal to just minus K1 times CA minus K2 times CA. And RB, since B only participates in the first reaction, is K1 times CA, and RC would then be K2 times CA because it only participates in the second reaction. Now, once we have the rate laws, we put those in our mole balances. And of course, for a batch reactor, our mole balance is just dNi dt is equal to Ri times V. And of course, we know that there's a relationship between moles, concentration, and volume. So this is just dCiV dt is equal to RIV. And in this particular problem, we were operating the reactor at constant volume. So if we divide both sides of this equation by the volume, we get dCi dt equals Ri. And then that allows us to write mole balances for each of our species. And so that means that dCa dt is just equal to Ra, which is minus K1 Ca minus K2 times Ca. dCb dt equals K1 times Ca, and dCc dt equals K2 times Ca. And on our previous attempt at solving this problem in lecture 6, this was a relatively straightforward thing to do because K1 and K2 were constants. And when we treat them that way, we could just group the terms and then integrate very easily for Ca. But you can't do that in this case because these are also going to be changing with time because the temperature of our reactor is going to be changing with time. So if we have to determine the temperature, we need another equation to do that because our unknowns here are Ca, Cb, Cc, and T. And that's where the energy balance above comes into play. And so if we think about our 4 unknowns, we need 4 equations. So there's 1, 2, 3, and 4. Now, how do we actually apply this equation above, the result of our energy balance, to the system at hand? So first of all, I want to draw a distinction between this example and the next one that we're going to solve. So here we have 2 reactions that are happening, but they're both included in Ra. And so we're going to be able to treat this very, very simply, right? Ra is just going to be able to go into there. So that's fine. That shouldn't be an issue. The next example we're going to solve, that is not the case. And we'll talk our way through that just a little bit. The other issue in this problem is really this term and implementing our assumptions that we have. So I mentioned just a moment ago that the moles are essentially just water, right? So Ni really is just water in our system. We have some contribution of whatever A is at the beginning and what B and C are as you move through the reaction, but it's overwhelmingly water. And so if we think about it this way, right, that Ni is approximately just N water, well, we really then can just say, look, the number of moles of whatever is in our system is just the mass, which is the density times the volume, divided by our molecular weight. And if it's water, of course, we're going to use 18. So in this particular case, we're going to say that Ni is basically a constant, right? So the density of water is 1.08 kilograms per liter times our volume. And we were told in our problem that the volume is 3 liters. And we know the molecular weight of water is 18 grams per mole. And we just have to do a quick unit conversion because we have kilograms and grams. So we know that there's 1,000 grams in a kilogram. And so our number of moles here of water is 180 moles. Okay, so that term in the bottom here, Ni, is essentially 180 moles in this problem. Now, that brings up a secondary consideration here, where we were talking also in our problem statement about the heat capacity and how it is that we're going to implement the heat capacity in this particular problem. So the way that I chose to do this was to take the heat capacity expression from a thermo textbook from Smith, Van Ness, and Abbott. And I ended up using that Cp over R equals A plus Bt plus Ct squared. So, we obviously have a more complicated function here for the heat capacities. We also have to remember how temperature gets implemented in our reaction rate constants. And so for either of these, remember that, Ki is equal to, at some temperature, is equal to Ki0 times the exponent of minus Ea for that reaction divided by RT. And so if we were looking for two different conditions here, well, we're not actually given Ki0 in this problem statement. We're given the activation energy, and we're given the value of the reaction rate constants at a specified temperature. So one of the things that we can do when that's the case is say, well, I know this is Ki at T2 equals Ki0 times the exponent of minus the activation over R times T2, and then just divide that by the same expression at a different temperature, right? So then that's Ki at T1 divided by Ki0 times the exponent of minus EAI over RT1. And in that case, the pre-exponential factor goes away, and we're left with an expression for either of the reaction rate constants at another temperature is equal to that reaction rate constant at the temperature we know, which in this case is 250 degrees C, then times the exponent of EA over R times 1 over T1 minus 1 over T2. Okay. So at this point, I would like to point out the complexity in the equations that we need to solve. That they look relatively straightforward, especially these, but think about every single one of these has to have an expression that looks like this in it, which is also a function of temperature. We have our derivative with respect to temperature also has these buried in it because they're in the rate constants, right, which are in here. Function that, of course, there's no analytical solution for. And so during the course of our semester is solve problems in Excel using Euler's method. And of course, Euler's method is essentially converting the derivatives into deltas, and you just have to pick a small enough time difference that your solutions don't get unruly. And that's one of the things that can happen. In fact, even when I was solving problems for homework 4 last week, I had a situation where I changed one of the variables and the solution exploded. It said the temperature was going to be 1,000,000 Kelvin, which of course we know it can't happen. Well, I mean, it can on the sun, but that to me said, oh, I didn't take a small enough time step. And so I had to take smaller and smaller steps. So that's also how we are going to go about, how we would go about solving this particular problem, where we're going to convert each of these into deltas. Now, we've done that a lot of times. So I'm not going to write out the very, very long form for the answer with all the deltas in it, because I actually believe that you guys can do that relatively well. But what I would like to do is, again, to show you how I've organized the Excel file in order to solve it in an organized way by Euler's method. And so you'll notice at the very top of this Excel file, I have the information regarding reaction 1 on the left-hand side, the upper left-hand side, and reaction 2 on the upper right-hand side. I also have our initial temperature we're given, the initial concentration, our heat transfer coefficient times the area, the jacket temperature, the information to calculate the heat capacity as a function of temperature, right? Just the coefficients. And then I have the other constants that were given. So we were given the density, the volume, and then here's my calculated number of moles, just using that, just using the equation that we used a second ago. I have a delta T in seconds, which is every 0.1 seconds, and then of course the units of time are going to change about every 0.1 seconds, or every row in this Excel file will change by 0.1 seconds. And then you'll notice that just like in lecture 14, when I showed you the Excel file for a non-isothermal problem, I essentially always have the temperature equation come next, because so many things are going to vary with temperature. In this particular problem, K1, K2, the heat capacity, these things all change with the temperature. And of course, we're told that actually in this problem, we're going to assume that it's 10% higher than the heat capacity of water. So really, we're interested in Cp of water times 1.1. Then from there, I implement the mole balances, A, B, and C. And then I calculate the conversion. And because we're talking about selectivity and yield in lecture today, I've also calculated the instantaneous selectivity and the overall selectivity here. And you'll see, of course, that in our cells here, right, these are just the equations that we derived a minute ago. It looks a little complicated in the function bar at the top, but really here's just dt or delta T times our function, right, plus the previous temperature. And here's how we calculate K1. If you look at the function bar, it's basically our initial value that we had times the exponent of EA over R times 1 over T1 minus 1 over the T that we are presently at. And the same thing for T2 and our ability to calculate the heat capacity. The nice thing is when you use a program like Excel to do this, our mole balances still look relatively straightforward, right? Our mole balance here is still just delta T times RA plus CA, the previous CA. So I like doing that, and I like keeping the equations as implemented as simple as possible. And what I mean by that is I want them to still look like this in Excel. I want it to still look like this in Excel. And so you'll notice that when I set up the file, I have independent cells to calculate K1, K2, and the heat capacity, and 1.1 times the heat capacity. And I do that because if I make a mistake with a negative sign or something, it's much easier for me to find it that way. It's also just easier for me to implement one equation at a time. I don't know about you, but I don't like to implement enormous equations. And so I try not to do that as much as possible. So we have just applied the equations that we've derived previously to this. We've implemented it in Euler's method. Now, what does that mean, or what is the result here? Well, the first thing is that we calculated the reactor temperature versus time. So we started at 25 degrees C, and eventually the reactor heats up over time to about 250 degrees C, which shouldn't be a surprise. That is our jacket temperature. And you're going to notice this when you solve non-isothermal reactor problems with a jacket. Eventually, most processes just lead to the jacket temperature. That's really the point of the jacket. It's, yes, you're going to add heat or remove heat. That's really great. But what you're trying to do in the jacket is set the temperature. And one of the things that you can see here is that it takes a while to get to the jacket temperature. And one way that we could adjust that is by changing the heat transfer coefficient, for example, by a different material or a different thickness of the same material. It also, if you know that the heat transfer coefficient isn't high enough to get to the design point that you want, you also could over-design the jacket. So you could go to a higher temperature, hoping then to get to your set temperature maybe a little bit earlier. Okay, and what does this mean for the reactant concentrations versus time? Well, The solution that we had the last time in lecture 6 is here on the left, when we knew what the reaction rate constants were and we are already operating at 250 degrees C versus waiting to get there. And you can see very, very clearly that the reactions initiate much more slowly. That in this particular problem, the conversion of A in when we consider temperature effects, when we've started at room temperature, it just takes a little while for the reaction to go. So your conversion is definitely lower as a function of time in this non-isothermal case where we're just starting up the reactor from scratch versus when everything was already perfectly heated and at isothermal at 250 degrees the entire time. And if you look at that, the influence that it really has here is on the concentrations or the relative concentrations of B and C, not just on how A or how rapidly A is being consumed. And of course, if we look at, the concentration of B is slightly below the concentration of C at the beginning, which is really interesting, right? That what's happening is that the second reaction is outcompeting the first one at these lower temperatures. And that's even something we talked a little bit about in lecture 6. And if you remember in lecture 6, in this particular problem, because the selectivity was really just K1 over K2, when you're isothermal, that meant that the selectivity was equal to a constant. And you can see that here, that we were a little over 1.5 when we did this example in lecture 6. But now, when we look at the selectivity, not only is it not constant, but also the instantaneous versus overall selectivity are changing with time. That wasn't the case in lecture 6. Those two were equivalent to each other. And because of these lower temperatures that we're operating at the beginning, you can see that the selectivity and both the instantaneous and overall selectivity in our process are very, very poor, where B was our desired product. And you could have guessed that probably here just by looking at the concentrations. So when we have a design point where our reactor temperature is 250 degrees, we can solve the problem like we did in lecture 6, where we say, well, we're going to design this thing to be operated at 250 degrees C. And here's how that's going, here will be the result. And we would have expected the selectivity to be constant over time in a certain value and have a certain expectation for how long I need to run the reactor. But in this batch reactor, where we started at room temperature, which quite frankly, unless you're going to preheat the reactants separately and then add them to the vessel, is very representative of reality, where you would start the reactor at a lower temperature initially, and then allow the jacket and then the heat of reaction to contribute to, assuming of course that it's exothermic, to heating up the vessel over time, or to heat the reactants over time. You can see that nothing that we did in lecture 6 really holds when you take this thermal drift or the time that it would take to heat up the reactor into consideration. And so one of the things, as you guys go back through this when you're studying, or even when you're doing the homework problems on the non-isothermal reactors, think a little bit about what are the variables that you might adjust to increase the selectivity here. And in lecture 6, we talked about using temperature, right? And that's obviously working here. That as the reactor heats up, the instantaneous selectivity is getting pretty high. And you'll notice that the instantaneous selectivity is becoming equivalent to what we solved for in lecture 6. It's about 1.5. But the overall selectivity, we never get there. And so if we want to improve the overall selectivity, there are a number of things to do, right? We could go to a higher temperature. We could change the rate of heat transfer by doing certain things with our reactor design. We talked about preheating the reactant, so that way we start at a temperature that's at least a little closer to where we might have. You might be able to do that either heating them separately, or maybe what you do is you heat up the vessel. So that's one thing that we haven't talked about at all in our class, and it's something that we're not going to talk a lot about. In a CSTR or in a plug flow reactor where you're operating at steady state, you've actually already set the temperature of the reactor over time. So you don't have to worry about problems like the heat it would take to heat up the reactor. In this case, you do have to worry about that, although we didn't take the heat capacity of the tank into consideration. Now, if you were to do that, it would go here, actually. It would go here in the denominator. Now, like I said, it's something we haven't talked about. It's not something that we're going to do right now. We're focused on in this particular lecture. But one of the things you could do is that if we have a large solid reactor, well, you know that solids have higher heat capacities than gases and liquids. So you could always just heat the solid. You could get the jacket to warm the reactor itself for some time before the reaction occurs. And then maybe you put that in and then you get a little bit of heat transfer immediately from the solid. And then you have to heat up both the solid and the liquid over time. So, and maybe how you stir the reactor plays a role in that, et cetera. There's a lot of things that we could think about here. But, you know, as you go back through this, you know, in addition to some of the things that I just talked about, it would be really helpful, I think, for you guys to talk yourself through this. You know, what could we do? And how could we manipulate variables to improve things like selectivity? Okay. All right. So that's our first example. I know there was a little bit of Food Network magic in there where we said, ta-da, here's the solution because we use Euler's method. But does anybody have any questions about how we implemented the energy balance, how we implemented the mass balances, or any of the plots that I showed? Okay. If not, let's move on to a second example. And this one should also look quite familiar. So here, we're going to look at reactions in series. And so we have A goes to B goes to C. And we're going to assume in this problem that both reactions are very endothermic. So we have delta H of reaction for both reactions, A to B, with the reaction rate constant K1, and B goes to C with the reaction constant K2 here on the right-hand side. And we can see that they're both endothermic. We're going to assume that the heat is provided through something called a firebox, whose temperature is stable at 875 degrees C. Now, this issue about a firebox you've probably never heard of before, but one of the things that happens in large reactors, so let's just take, you know, a large, reactor, whether it's a batch reactor, it could be a batch reactor, it could be a CSTR, it could even be a PFR. But one of the things that they'll do in assembling these reactors is that it's really hard to jacket them and to be able to assume that you have enough sort of thermal diffusivity for the temperature to be constant on the inside of the reactor. So one of the things that's done often instead is that they'll have large tubes that go through the reactor. And I really wanted that to be a little bit bigger. Let me see if I can fix that. All right, so there we go, that's better. All right, so they'll have large tubes that run through the reactor. And what you'll do here in the space is you'll like burn methane or some other fuel. And I'm just going to write burn methane. I'm not going to try to draw fire. I know my artistic limitations. So you're going to do the same thing here, and you're going to do the same thing here. And essentially what you've done is at this temperature, you've increased the surface area that's exposed to the gas phase reactants inside. So you can transfer heat faster and try to maintain, either an isothermal operation or add heat at a rate that you're interested in. And so you'll, exchange heat in all directions here with the inside just by burning methane. And sometimes, there's at the bottom, there's literally fire in the column, right? You'll flow oxygen and methane. It hits this really hot reactor and it'll ignite. And then you have a flame that goes some way up the tube. And then the rest of it is just hot gas. It'll be CO2, water, and whatever, excess nitrogen, oxygen from air is just hanging around. Okay. So, just FYI, when I say an internal firebox, that's the thing that I'm talking about. Okay. So we're heated. That gas is approximately at constant temperature, which is 875 degrees C. We have our value for our area times our heat transfer coefficient. We have the initial concentration of A. We know the volume of our batch reactor. We're given a constant heat capacity for all of the species, and we're given the initial temperature here. So let's have a look at, first of all, our original solution where A goes to B. And I want us to, isothermally with these reaction rate constants of 0.06 and 0.04. So here's what we derived in lecture 5, right? And this was our solution. And hopefully this rings a bell. And what we saw was that our optimal concentration of B occurred at about 20 minutes of reactor time. And we had a yield that started at 1, and then the yield decreased over time as B became C. And after about 100 minutes, we reached a fairly high conversion, and we stopped operating the reactor at that point. Okay, so that's where we were in lecture 5. So now 10 lectures later, we're thinking about the same system, but now it's not behaving isothermally. So let's have a look at this. And if we remember our mass balances, right? Well, we know that RA, of course, is just minus K1 times CA. And this is, A goes to B, goes to C, and that's K1, that's K2. RB is K1CA minus K2 times CB, because we formed that through the first reaction and it's consumed in the second reaction. And RC equals K2 times CB, because you only form it in that reactor. And remember, for a batch reactor, or that reaction, in a batch reactor, dNI dt, right, was equal to Ri times V, and at constant volume, just like we did a moment ago, that becomes dCi dt equals Ri. And that means that essentially our mole balances are just this, right? dCa dt is K minus K1Ca, dCb dt is K1Ca minus K2Cb, and dCc dt is K2 times Cb. Okay, so those are our mole balances, and those should look familiar. That's exactly what we had in our previous lecture. And remember, what we did in lecture 5 was we first solved this one, then we ended up plugging that into this equation and solving that equation, solving for Cb, and then plugging that in here and getting the concentration of C. Now, of course, again, the non-isothermal part of our design makes this a little bit more complicated, because our result of dC dt equals UA times T star minus T plus RAV times delta H of reaction divided by the sum of NI CPI is complicated, and for the same reasons it was in our previous example, except there's another hiccup here. One of the problems that we have is in this term, is in RA. So if you remember, we derived this by making an assumption in the last lecture. We got there because we had a point in our derivation where we had HI times DNI dt, and we said that that was equal to HI times RA times the ratio of the stoichiometric coefficients. Now, That's fine for one reaction. But if you look at what's going to happen here, is if we have multiple reactions, that doesn't account for reaction 2 because RA only has the first reaction in it. And so this expression here was generalized for one reaction. Okay. And so what I would like to do is revisit this for multiple reactions. And if you go back to your notes from lecture 14, that our initial result for the energy balance was that the sum of dNi HI dt equaled UA times T star minus T. And then what we did was we used the product rule and we got the sum of Ni dHi dt plus Hi dNi dt equals UA times T star minus T. And then we did a couple things, but one was we put this in here. Well, in this case, we're not going to do this, okay? Because we have more than one reaction. So the question then is, what are we going to do here? How are we going to actually implement HI times dNi dt? And let's of course not forget that this term here, right, is just CPI dt. So we're going to make the same substitution here we did in lecture 14, but we're going to reevaluate this because we have multiple reactions. So if we have multiple reactions, then we really just need to look at this sum of HI dNi dt. Now, remember above, right, dNi dt is just equal to RIV, right? That's just the mole balance for a batch reactor. And so this term here, the sum of HI dNi dt just becomes equal to the sum of HI times RI times V. Well, let's directly implement this for all of our reactants. So this is really the enthalpy of A at our temperature times RA times V plus HB times RB times V plus HC times RC times V. So then let's just plug in our rate laws. And that becomes HA times minus K1CA times the volume plus the enthalpy of B times K1CA minus K2CB times the volume, then plus HC times K2CB times the volume. All right. Now what we can do is group some terms, because we see we have things like K1CAV both here and there. And we have K2 times CB times V here and there. And so let's just group those and bring those out front. So we're going to say that that's equal to K2. Here, I was doing that in red. Let me continue to do that in red. So that's going to be equal to K1 times CA times V times, now our two terms, right? This is just HB minus HA. And then plus K2 times CB times V. And we only have two terms for that as well, right? That becomes multiplied by HC minus HB. And if you look at this, the enthalpy at B minus the enthalpy of A, this is just delta H for reaction 1, right? At our temperature. And this is just delta H for reaction 2 at our temperature. And so we get an expression here, then that's just equal to K1 times CAV times delta H of reaction 1 plus K2 times CB, not CA, times V times delta H for reaction 2. And this should feel good, I think, for us to get this answer. You know, now we have that term in variables that bring both reactions into play, and nothing looks foreign, right? Nothing looks unusual. So now we're able to put this in our mole balance or in our energy balance and make the same substitution that we made there before. And so when we do that, we have our energy balance, which is that dt equals UA times T star minus T minus K1 CAV times delta H for reaction 1 minus K2 times CB times V times delta H for reaction 2 divided by the sum of Ni CPI. Okay. And we know how to implement all of these because we have Ni, or we will use the Ni this time from the mole balances as we solve for them. And we were given the heat capacity for each of the species. We were told that they were constant and that they were equal to 4 times R, right, in this particular case. So we should be able to do the same thing that we did a moment ago and implement this in Excel using Euler's method. Now, the warning I'll give you is units, and we talked about this before, that we're given 1 unit for K, right, for the Ks here, and we're given a totally different unit for UA, right? So we have, this is in watts per Kelvin, right, which is a joule per second Kelvin. And our Ks, you know, K1 and K2, if we go back to the problem statement, are given in minutes, in inverse minutes. And so as we implement the problem in Excel, we're going to have to take that into consideration. And so, you know, here again is my Excel file that I used for Euler's method in this particular problem. So at the top is the information for reaction 1 and reaction 2. I have all the knowns, right? Ca0, the initial temperature, our heat transfer coefficient times the area. And you'll notice, actually, I have 2 cells. I have 1 in joules per minute Kelvin, and then I have just a check to make sure that I calculated that correctly. I have the temperature of the jacket in Kelvin. I have the volume of our reactor in liters. I have the heat capacity for all the species as Cp over R, but of course we need the heat capacity in joules per mole Kelvin. So I just multiplied by R here. And the sheet here is set up very similarly to the previous one, where delta T is here, then we calculate times, then temperatures, then the rate constants at those temperatures using the exact same equation we used in the previous example. And then using the mole balances, I find the concentrations of A, B, and C. I find the conversion, right? In this case, the volume's constant, so it's just 1 minus Ca over Ca0. And I also chose to calculate the temperature in Celsius, and then I calculate further to the right here the selectivity and yield. And so let's have a look at this. So remember, this is what our solution looked like previously, okay, where we had our concentration of B peaking at about 20 minutes. The first case that I solved, which I think is interesting, maybe to talk about very quickly, is the adiabatic case. And that's where UA was equal to 0. So I did that very quickly in Excel, even though it wasn't asked for in the problem statement. I thought it would be interesting to show. And if you see what happens, that the concentration of Ca really doesn't change very much. at the beginning, when the reactor is sort of warm, some reaction occurs, but the reaction is so endothermic that you can see it's quenched. So look at the temperature here on the right-hand side. So the temperature drops very, very low, and essentially there the rate constants are 0. And so almost no reaction is happening there as a function of time. So I thought that was interesting, and it actually lends support for the need to have a jacket in this case, or really in this case, the firebox, which is behaving like the jacket. Now, for the problem that was actually asked, where we had the heat transfer coefficient, which was 19.8 watts per Kelvin. So here I converted that into minutes, and that's 1188. So one of the things that you can see here is that, first of all, the reactor takes quite a long time to reach the same peak concentration of B. So here the peak concentration was a little less than 1. Here it's a little more than 1. So our peak concentration of B is higher, but it took much, much longer to get there. And we can see at the plot on the right-hand side that it's a thermal effect, that the temperature is dropping very, very quickly, and it takes the firebox quite some time to start to warm the reactor back up. So you can see that on the right-hand side, where the temperature drops, right to about 500 degrees C when you enter the reactor, and then the conversion kind of stalls a little bit. It goes up very quickly at the beginning, and then it kind of lazily increases. And then as the reaction rate becomes slower than the heat transfer rate, the temperature can recover. So that was here. Now, one of the things I thought of when I was doing this was, well, what might we want to do in this case? Well, we might want the reaction to happen a little bit faster. So what if I made the heat transfer coefficient much higher? So I got a little ridiculous here. I went from 1,000 to 100,000. UA of 100,000, you're not going to get to by, increasing the number of tubes or making them out of another material. But what happens here is that at really high heat transfer coefficients, you can see that the reactor temperature is pretty constant here on the right, and the solution becomes a lot more like the isothermal case. So the higher the heat transfer coefficient, the more that it's going to behave like the isothermal case. And that's something to keep in mind later when you're actually, if you're ever doing reactor design. We also can compare then the yield of B when we have the lower heat transfer coefficient versus the higher one. So that's on the left and right respectively. Now, I looked at this plot and thought, okay, well, that's really interesting. It kind of looks like the lower heat transfer coefficient would be preferred because at the same reactor time, you get a higher yield. But remember, the conversion is changing here, right? In the reactor on the right-hand side, the conversion of A is much higher at all times. So I actually thought a more fair way to look at the yield is not the yield versus time, but it was the yield versus the conversion, and to see, where you get to and how you might want to operate the reactor. And one of the things that you can see here is that just like our initial solution, the overall yield at the beginning is 1 and it drops, right? So here was our original solution. But for our case where we start with a lower heat transfer coefficient, the yield is higher for most of this plot. In fact, it's essentially the entire plot. And one of the things that's happening here in this reactor is that with a lower heat transfer coefficient, the first reaction is preferred for a longer time. And so you have a much better yield of B than you do when you're operating more isothermally, which is the case here on the right-hand side with the really high heat transfer coefficient. And so, this brings up its own interesting questions about how you might design the reactor in a case where, you might want a higher yield of B, but you're trying to balance the reactor time with the yield. And it's an interesting interplay between temperature and these variables that we haven't really thought of before because we always assumed that it was isothermal. And there's all sorts of interesting things that we can do. One is to manipulate the heat transfer coefficient, of course, but we can do other things like manipulate the jacket temperature. We also could think of throughout our class so far, we've only considered a constant UA or a constant delta T. Well, what if you could meter the rate that you introduced heat into the reactor? So you could get the reactor to a temperature where the reaction still progresses fairly rapidly, but you never get into a case where the instantaneous yield is very, very low, or the instantaneous selectivity is very low. And so when you start to look at these cases where the temperature doesn't change, or there's not a lot of interesting dynamics. But now when we're starting to look at what happens when the temperature does change, it brings up all sorts of interesting questions where creativity in reactor design can be really, really helpful, and thinking about modes of operation for a reactor that you might not have thought of previously.